Hello class, here's an example on writing equations for shear moment diagrams, and what you have to do is you have to write the equation for each section, and then we're going to draw the shear moment diagram of the beam shown. So I've already computed the reaction forces of AY and DY. Now if you wanted to pause the video and compute these really quick and check them, that would be great for practice. Now I have already started, to save some time on the video, I have already started drawing the free body diagrams of the each section. So what you'll see here is from section A to B, which would be from here to right before B. And then A to C would be from A to right before C. And from A to D again would be right A to right before D. So for each one of these sections, you're going to have to compute a distance called x distance. So what we're doing is we're trying to find the shear and moment anywhere between A and B, and that's what we have to write our equations for. So we were given that this is a 50 kilonewton per meter distributed load. Now if I'm to draw my shear and moment, I would show my shear, which is going to be shear from A to B, and then my moment, which is going to be moment A to B. And then again we just use our equilibrium equations to solve. So I'm going to sum my forces in the y direction. And when I sum my forces in the y, I've got 90 kilonewtons, which is going to go up, so it's just positive. I have this 50 kilonewton per meter, so it's going to be negative 50 kilonewton per meter. Now remember, these are all, this distributed load is pushing down. But what else do we have to do? Well, in order, if we were using the point load, if we were converting this to a point load, we'd have to multiply by the distance. So in this case, our distance is x. Then we have our shear, which is going to be minus shear AB, is all equal to 0. So if I just rewrite this by taking my shear to the other side, I get shear from A to B is equal to 90 minus 50x. We're going to forget the units just to make this cleaner for now. Now if I sum my moment, and I'm going to do it, we'll call it point B, about that point right there. So if I'm summing my moment about point B, I'm going to have 90 kilonewtons times x. Remember, it's 90 times this distance is x. Now this is going to rotate positively, so this was negative, so it's going to rotate clockwise. Then I'm going to have plus 50 kilonewton per meter times, now if we're doing the distributed load, that point load again is just like what we did up here, that's going to be x. But since we're doing a moment, this distance that we're looking at would be half the distributed load, which would be x over 2. And then we have our positive bending moment, which is all equal to 0. So by doing a little algebra, I take all of this to the other side, so I'd have MAB equals 90x plus 50x squared over 2. Now we can see that will actually be negative since I took it over to the other side. And what we could also do is we could do some stuff here. So MAB could actually be, and I'm going to put the x squared first, that's just kind of how I like to write it. So it's going to be 50 divided by 2 x squared plus 90x. So now we've got our equation for moment and our equation for shear from section A to B. So now let's try excuse me, A to C. So again, always starting with our distance from the very left point is going to be x. So this distance is x, and we know this distance is 2 meters from here to here. we have the same distributed load here, so it's going to be 50 kilonewton per meter, and we know this is going to be sitting right in the middle there. So we also have our reaction force, which was 90 kilonewtons. Let's draw our shear. Our shear is going to be from A to C now. Actually, I'm going to re-say that. It's not from A to C. When we do it this way, it's going to be from point B to point C. That's what we're looking at here when we're looking at this equation. And so this is going to be shear from B to C, because remember, we did already A to B, A to B. Now we're doing B to C, and then the last one here we're going to be doing from C to D. So here's my moment from B to C, and then I just do the same thing. I sum my forces in the Y direction. When I sum my forces in the Y here, I'm going to have negative VBC. I'm going to have 90 kilonewtons, which is going to be going up. And then I'm going to have, let's see, 50. We know its distance. So the point load here, and that's a little confusing. I'm going to do this. The distributed load was 50 kilonewton per meter. This would actually be 100 newtons here. So we'd actually subtract 100 newtons. It's all equal to 0. So our shear would then be, take this to the other side, that's going to be positive, and then I'm going to have 100 plus 90, which is going to be negative 10 kilonewtons. Now that just comes out to be no variables in there whatsoever. So if you look in here, there's no distributed load, so we know that the shear is going to be, so when we draw our shear diagram, we know that this is going to be negative 10 all the way through here. So by summing my moment then, and we'll do it about point C right there. I'm going to start from here, so this is going to be 90x, because it's 90 times x, and that's going to be a negative since it's rotating clockwise. And then I have this 100 newton meter, or 100 newton, I guess this is kilonewtons, 100 kilonewton force acting right here, so that's going to be acting positively, but we're going to have 100 kilonewtons. And this distance, we know this distance is going to be 1. So that distance there then is going to be 100 kilonewtons times x minus 1. Okay? And then I've got my moment, which is going to be plus MBC. Alright? So that's going to equal to 0. So let's see if I got this right. So I'm going to multiply this out, so it's going to be 100 times x minus 100 minus 90x plus MBC is all equal to 0. So here I'm going to get 10x minus 100 MBC. So I'm going to take this over to the other side. Let's do this first. We're going to know that this is 10x minus 100 plus MBC is all equal to 0. So now if I take this piece over to the other side, I get MBC is equal to negative 10x plus 100. So now I have my excuse me, my shear and my moment equation from B to C. So the last one that we have here is going to be from, let's probably should label those points in there. This is B and this is C. So we're going to be doing from C to D. So now we're looking from A to D. You notice I've already added a few things. I've added the point load, and our point load, well actually let's just show our distances first. Longer. This whole distance, again, as I stated before, our distance from the left hand side is always going to be x. And then we can go show the distances that are known between A and C here. So we both know that that's 2 meters and that's 2 meters. So this point load is going to be 50 times 2, which is going to be 100 kilonewtons. Now this distributed load, this distance here is going to be x minus 4. So this is going to be 20 kilonewton meters times x minus 4. So let's go ahead and sum our forces in the y direction. And we're going to have 90 kilonewtons, which is positive, minus 100 kilonewtons. And then here we also have a negative, so this is going to be a negative 20 times x minus 4 minus my shear from C to D is all equal to 0. So we know this is going to be negative 10. This here then, I'm going to subtract 20 times x. Now negative 20 times the negative 4 is going to be plus 80 minus my shear from C to D is equal to 0. So negative 10 and 80, that's going to be negative 20x plus 80 minus shear from C to D is equal to 0. So shear from C to D is going to be negative 20x plus 80. That's 80, I'm sorry, that's 70. Because negative 10 and 80 is going to be 70. Okay. So now let's do the moment. So the moment at point D is equal to 0. Starting over here again, I'm going to have a negative 90x. Here I'm going to have a positive 100. And now this is going to be, this distance again is 1, right there. So this is going to be x minus 1. The next one is going to be this point load here, which is going to be also a positive 20x minus 4. Erase that. 20x minus 4. And then we have to go halfway through. So what we're doing is we're looking at this distance right here. So that's going to be, if this is x minus 4, it's going to be half of x minus 4. So that's going to be 1/2 of x minus 4. Plus the moment from C to D is all equal to 0. So now let's clean up some of this stuff. So I'm going to have negative 90x plus 100x minus 100. Now here, if I'm saying 1/2, I can make that 10. So that's going to be 10. Move that away. This is going to be plus 1/2, so that's going to be 10. So then I'm going to have x minus 4 times x minus 4 plus MCD. So here I'm going to have, let's just do this. This is going to be 10 times x squared minus 8x plus 16 plus MCD minus 100 plus 100x minus 90x. A lot of stuff in there. So let's clean this up. I'm going to go get, I have to multiply this 10x squared minus 80x, and this was 16. Sorry, 16. So it's going to be plus 160 plus MCD is equal to 0. Write all this out again, and I'm trying not to take too many shortcuts in this. So I've got negative 90. Let's do all of our. So we have. Let's just do this. I have 10x squared. 10x squared. Sometimes if I have so much stuff in there, I'll kind of do this. Cross that out. So I've got 10x squared, and then let's do all my x's. So I got 90, negative 90. I've got 100. I've got negative 80. So I'm going to have negative 70 x, and then I'm going to have 100 plus 160. So I'm going to have plus 60 plus moment from C to D is all equal to 0. So now I can take this over to the other side. MCD should be equal to negative 10x squared plus 70x minus 60. Let me just check myself. Negative 10x plus 70x minus 60, and that's it. And again, this would all be kilonewton meters if you want to do the units on the outside, which is a great idea. So there we go. We have the equations. We have our equations now for each section of the beam. Now let's go in and go ahead and write out our shear moment diagrams. So here we're going to go up 90, and here I note my units, so I'm not going to write them in here. Now along, I'm going to scroll up just a little bit. Now along this beam, I have this distributed load, so I know I'm going to be going 2 meters times 50, so I'm going to be going down 100. So I'm going to land up at negative 10 kilonewtons. Then nothing is happening on the beam from here to here. And then I have another distributed load, which I know I'm going to be going 20 times 2, which is 40. I'm going down 40. So if this was negative 10 here, I went another negative 40. I got negative 50 kilonewtons here, which with my reaction force here closes. Now a couple of ways you can find these distances. So I'm going to need this distance here, and I'm going to need this distance here. Now one thing we can do, since we're between A and B, we can come back up here and we can set this up. So we can say, okay, when the shear is 0, so when the shear is 0, that's going to equal 90 minus 50x. So take the 90 over, so you'll or the 50 over, so you'd have 50x is equal to 90. We'll call this x. And we'll say that x is going to be equal to 90 divided by 50, which is going to be 1.8. 1.8 meters. So this distance here from here to here is going to be 1.8 meters. So what did I do? Let's kind of review what I just did there. When the shear is 0, so when the shear is 0, I can go to the equation that I created and say if the shear is 0, which I wrote here, is equal to 90 minus 50x. X, the distance from this point to this point. I compute it, I get 1.8. The other way you can do it is if I say this is 2 minus x, I can use a ratio. So I could come over here, I'll just do the ratio over here, where I'm going to have 90 to x is equal to 10 over 2 minus x. So let's compute this out real quick. That'd be 180 minus 90x is equal to 10x. So I take this over, so that's going to be 180 is equal to negative 90 plus 10 is going to be 100x. X, 180 divided by 100 would be 1.8. So x is 1.8, either this way or computing it this way. So now our areas then, our areas would be 1.8 times 90 divided by 2. I get 81. In this little triangle here, I'm going to write it out here, I'm going to have 10 times, so that's going to be 10, times 2 minus 1.8, which is going to be 0.2. So you multiply that and you divide that by 2, you get 1. Here I've got negative 10 times 2, which is going to be 20. And then over here I've got, break this up into 2. So I'm going to have 2 times 10, which is going to be 20. Let's just do it. 2 times 10, which is going to be 20. And then the triangle is going to be 50 minus 10, which is going to be 40, times 2 divided by 2, which is going to be 40, plus the 20. This is going to be 60 kilonewton meters. So I'm going to draw my moment diagram then. And since this is a negative slope, but it's going above, it's above, so it's a positive. So I'm looking at, let's just kind of shade that in. I'm looking at this area right here. So if I wanted to draw a line straight down, I'm not going to have a hard time doing that, but somewhere in there, I know that this shear is going to end up somewhere right here. So I know this is going to be 81, and since this slope is negative, I know that the curve here is going to be like so. As I move up and I draw the tangent lines, they decrease. You could also come over here and write in a bunch of x values, and you could plot this curve. So now I'm going down, but I'm only going down 1. So right here, I'm only going down 1, so I'm just going to kind of right there. So that's 80 kilonewton meters. Now I'm going linear, so I'm going to go 20. So I'm going to go down to 60 kilonewton meters, and that's going to be linear. And then again, I've got this distributed load is 60 kilonewtons. I'm below the x-axis, so I'm going to be going down. It has a negative slope, so I'm going to draw my curve that has a decreasing slope as well. So that would be your shear and moment diagrams. I definitely want to label, definitely want to label every point that you have on your shear moment diagrams. Sometimes it's nice to kind of highlight on your paper. I know I have a bunch of stuff here, but if you highlight, you kind of know where your shear and moment diagrams are. So let's just take a quick look right here. If I plugged in anywhere from A to B with this equation, and let's say I wanted to do 1. So if I wanted to do 1 right there. So I put 1 there, so that'd be 90 minus 50, which would be 40. You could say that that point right there is 40 kilonewtons. So if you say 90 minus 10, alright, so you go 90, you'd fall right in the middle there, that would be 40 kilonewtons. And you could do the same thing with your moment. Alright, now this is kind of a one to look at where you can kind of say, oh, okay, if I look at this equation here, and we're going from, again, from A to C, actually, I'm sorry, excuse me, retract that, going from B to C, so I'm going from this point to C. What's my shear? It's negative 10, so the whole way through it's negative 10. So here are the equations that match up with our shear moment diagrams, which you could plot, and that might help you out when you get into some more difficult beams. Alright, I know that was long, but thanks for listening.